There's a rule in astronomy that nobody ever states out loud because everybody in the field simply accepts it as true. If two objects sit close enough together in the sky and are similar enough in brightness, no telescope can tell their light apart. For nearly 40 years, that rule applied directly to Pluto and its largest moon, Charon, a pair of worlds locked so closely together that every infrared observation ever attempted blurred their signals into one another, making it functionally impossible to study Pluto's atmosphere on its own, separated from its moon, in any real chemical detail. In 2022, that rule broke. And when it broke, it did not just give scientists a clearer picture of a small, cold, frozen world at the edge of the solar system. It handed them proof of a climate system unlike anything else known to exist anywhere else among the sun's planets, moons, or dwarf planets, one that a scientist had predicted 5 years earlier and been told, by his own account, sounded like a crazy idea. This is the story of what the James Webb Space Telescope actually found when it finally managed to look at Pluto properly for the first time, why doing so should not have been technically possible with any previous instrument ever built, and why the answer turned out to be stranger than the initial prediction that inspired the search in the first place. To understand why this observation mattered so much, you first need to understand exactly how starved planetary scientists have been for new, detailed information about Pluto. In July of 2015, NASA's New Horizons spacecraft became the first, and to this day, the only spacecraft to ever fly directly past Pluto, capturing stunning close-up photographs of its heart-shaped glacier of nitrogen ice, its rugged mountain ranges made of frozen water, and its thin, hazy, blue-tinted atmosphere. But New Horizons was a flyby mission, not an orbiter. It passed through the Pluto system at more than 30,000 miles an hour, gathered as much data as it possibly could in the span of a single close encounter, and then kept moving deeper into the Kuiper Belt, never to return. Since that flyby, there has been no active mission anywhere near Pluto, and no telescope on or near Earth capable of resolving new atmospheric detail from a world so small, so cold, and so unimaginably distant, sitting roughly 3.7 billion miles from the Sun on average. Whatever new understanding of Pluto's atmosphere scientists wanted to build after 2015 would have to come from remote observation alone. And remote observation of Pluto has always run directly into that unstated rule about resolving closely spaced, similarly faint objects. Pluto and Charon orbit so closely together, separated by only around 12,000 miles, roughly the diameter of Earth itself, that from any reasonable observing distance they appear almost as a single blurred point of light in most instruments' fields of view. Ground-based telescopes could not reliably separate their infrared signals. Even earlier, space telescopes lacked the specific combination of resolution and sensitivity in the right wavelengths needed to tell exactly which portion of any detected heat signature belonged to Pluto's thin atmosphere and surface, and which portion belonged to Charon's airless, icy surface sitting right beside it. For decades, this meant one of the most basic and important measurements planetary scientists wanted. The specific mid-infrared thermal signature of Pluto's atmosphere alone simply did not exist. It could not be collected. The tool required to collect it had not yet been built. The James Webb Space Telescope was never designed with this specific problem in mind. Its primary mission, the reason it was engineered with such extraordinary sensitivity, was to detect the incredibly faint infrared light traveling toward Earth from galaxies formed in the first few 100 million years after the Big Bang, more than 13 billion light-years away. But that same extraordinary sensitivity, once turned toward our own solar system's outer edge, turned out to be exactly what was needed to finally crack the Pluto-Charon problem. Using an instrument called MIRI, the mid-infrared instrument, astronomers were able to resolve Pluto and Charon as two genuinely separate thermal sources for the first time in the history of astronomy, and in May of 2023, they captured a complete, high-resolution mid-infrared spectrum of Pluto's atmosphere, spanning a range of wavelengths that had simply never been explored before because the instrument capable of exploring them had never previously existed. That first successful separation of the two signals immediately answered a question that had been quietly debated in planetary science circles since 2017. That year, a researcher named Xi Zhang at the University of California, Santa Cruz, proposed a theory about Pluto's atmosphere that many of his own colleagues initially treated with open skepticism. Chang suggested that the layered blue haze photographed drifting through Pluto's thin atmosphere during the New Horizons flyby was not simply a passive visual feature, but was actually functioning as an active climate control mechanism, absorbing incoming sunlight and radiating that energy back out as mid-infrared heat. In the process, actively cooling Pluto's entire atmosphere in a way no other world in the solar system was confidently known to do. Zhang made his theory falsifiable by attaching a specific, testable prediction to it. If the haze really was cooling Pluto's atmosphere this way, it should produce a distinct, measurable mid-infrared emission signature, one that would only become detectable once an instrument sensitive enough to isolate Pluto's individual thermal glow, separate from Charon's, finally came along. Zhang has been candid about how his prediction was initially received, admitting plainly that it sounded like a crazy idea to many of his peers at the time. When Webb's MIRI instrument finally separated Pluto's signal from Charon's in 2022, the exact emission pattern Zhang had predicted 5 years earlier appeared in the data, matching his theoretical model closely enough that Zhang himself described the confirmation as something rare in planetary science, a hypothesis validated so quickly and so cleanly that his own research team felt genuinely lucky to have witnessed it. Pluto's atmosphere, the confirmed observations now show, runs on a haze-driven climate system unlike any other currently documented anywhere in the solar system, a mechanism researchers have described as bearing some resemblance to certain processes seen in the thick, hazy atmosphere of Saturn's moon Titan, but expressed on Pluto in a form distinct enough that scientists studying the results have referred to it, in their own published statements, as effectively a new kind of climate, one science had never directly observed operating anywhere else before Webb made this measurement possible. The same breakthrough in separating Pluto and Charon's signals also allowed researchers to finally confirm, with real chemical precision, something New Horizons had only hinted at visually back in 2015. Pluto's atmosphere is slowly leaking. A measurable stream of material actually escapes Pluto's thin, tenuous atmosphere and drifts across the roughly 12,000-mile gap separating the two worlds, eventually settling onto Charon's north and south polar regions, where it undergoes a slow chemical transformation into the strikingly dark, reddish material that gives Charon's poles their distinctive coloring, visible even in New Horizons' original photographs. It is one of the only confirmed examples anywhere in the solar system of one body's atmosphere physically raining down onto the surface of its own moon. A genuinely unique planetary relationship that Webb's improved resolution has now allowed scientists to study and quantify with a level of chemical detail that was simply unavailable before this specific technical barrier was overcome. And Charon itself yielded its own significant surprise once researchers were finally able to study its surface in isolation, free from Pluto's overlapping signal. In a study published in October of 2024, a research team led by planetary scientist Silvia Protopapa at the Southwest Research Institute used Webb's near-infrared spectrograph to identify carbon dioxide and hydrogen peroxide embedded in Charon's icy surface, two compounds that had eluded every previous instrument ever pointed at this distant moon, despite Charon having been known to astronomers since its discovery back in 1978. Protopapa described the significance of this finding directly, explaining that Charon's surface preserves physical evidence of its own formation through the presence of carbon dioxide, alongside clear signs of long-term radiation exposure indicated by the presence of hydrogen peroxide, evidence embedded in the ice itself of processes stretching back billions of years into the moon's earliest history. Protopapa's team has stated they intend to continue studying Charon with Webb going forward, specifically targeting gaps in the current data that could reveal even more previously undetected compounds hidden in its ancient icy surface. It is worth pausing to appreciate exactly what this entire sequence of discoveries actually represents, because it is easy to treat each individual finding as its own isolated headline without noticing the larger pattern connecting all of them. None of this, not the confirmation of Pluto's haze-driven climate, not the detailed chemical mapping of material transferring from Pluto's atmosphere onto Charon's poles, not the discovery of previously undetected compounds on Charon's surface, would have been achievable without first solving the basic, decades-old technical problem of separating two small, closely spaced, faint infrared sources from one another. That single technical achievement, resolving Pluto and Charon as genuinely distinct thermal objects for the first time in the history of astronomy, is what unlocked every discovery that followed it. It is the kind of breakthrough that rarely gets its own dramatic headline, because it sounds, on its surface, like a modest technical improvement rather than a dramatic new finding. But it is precisely the kind of quiet capability upgrade that, throughout the history of astronomy, has consistently been the actual mechanism behind the field's biggest leaps forward. Better resolution reveals details nobody could previously separate out from the noise, and those details, once finally visible, tend to reshape an entire scientific picture that had been built, until that point, on incomplete and blurred information. So should this have been possible at all, using an instrument engineered primarily to peer at galaxies existing near the very beginning of cosmic time? By the standards of every telescope that came before it, the honest answer is genuinely no, not with the level of chemical and thermal precision Webb actually delivered. Ground-based telescopes lacked the necessary resolution. Earlier space telescopes lacked the specific sensitivity across the exact mid-infrared wavelengths where Pluto's atmospheric haze signature and Charon's surface composition both happened to reveal themselves most clearly. It took an observatory built for an entirely different purpose, pointed at an entirely different kind of target, to finally possess the combination of capabilities needed to solve a problem that had quietly limited Pluto research for the better part of 4 decades. What Webb actually confirmed, once that barrier fell, was not some singular dramatic revelation delivered in one moment, but an entire cascade of previously inaccessible detail about a genuinely strange, genuinely unique small world sitting at the outer edge of our solar system. A climate system driven by an atmospheric haze behaving unlike anything documented on any other planet or moon. A confirmed, ongoing transfer of atmospheric material from Pluto directly onto the surface of its own largest moon. And chemical compounds on Charon's surface, carbon dioxide and hydrogen peroxide, that had remained completely undetected for the entire 46 years since that moon was first discovered, simply because nobody had ever possessed an instrument capable of finding them until now. Pluto has not changed since New Horizons flew past it in 2015. What changed is our ability to actually look at it properly, separated cleanly from its closest neighbor for the very first time in the history of observational astronomy. And what that first proper look revealed is a small, distant, frozen world running on a climate mechanism nobody had confidently observed operating anywhere else in the solar system, quietly confirming a theory one scientist had been told, just a handful of years earlier, sounded a little bit crazy. If you want to see what Webb finds the next time it turns its instruments back toward Pluto and Charon, subscribe and turn on notifications, because researchers have already said they are not finished studying this system, and there's clearly more hiding in that ice than anyone expected to find.